Hello everyone, welcome once again to my YouTube channel. Today we'll be looking at how to test our time series model to see how accurate it is by splitting the data set and testing it on the previous data set. Then we'll look at it, we'll compare what was predicted to what is actually there to test for the root mean square error to see how accurate the model can predict. Sit back, relax, and enjoy the teaching.
Okay, so today we'll be looking at how to check your accuracy of your model, your time series model, using mean squared error metrics. So that's what we imported here. So it's going to follow the same process as when you want to forecast on a normal day. But the difference here is that we're going to split our data set so that we'll train the model with one part of the data set, and the remaining part of the data set will be used to test the model. Then we can now determine our mean squared error. Don't forget, in our linear regression model, we had a result for our root mean squared error. So when we get the result for this, we'll compare it with that other one, and you will discover that the linear regression or support vector regression models are far better than this time series model for this data set. Links will be dropped in the description to the other videos which I'm referencing. So we import our libraries, then our data set is loaded. We do the same thing. We convert our date column to date and time, to date time. Then we check for stationarity in our data set. We apply the differencing. Then we rerun the ADF test on it again. And we can see this is the value. It's just the same process. Okay. So since it's now stationary, we do the same thing. We plot to check for our parameters for our ACF and PACF. So plotted the chart is just the same, like when you are just forecasting. You are actually forecasting. It's just that we're dividing the data set. So let's proceed. So now we define our parameters. So we decided to range between 0 to 3 because most of the time it's not beyond 3. Most of the time, the value you get for your P and Q, which are your AR model and your MA, your AR term and your MA term, most common number is 1. But because of the data set, we want to choose the best. So that is why we go through the hyperparameter tuning. So we tune our parameter and we came up with these values. So with these values, we trained our model. So now look at where the difference is. We split the data set into the training data, the data we'll use to train the model, and the data we'll use to test the model. Now, what did I do? I split the data into 2. Now, this number means from 0, that is from row 0 to row 1460. That is the meaning. So it tells us that from year 2020, because our data set starts from year 2020 to year 2024. So it says, from January 1st, 2020 to December 31st, 2023, put everything in this trained data. So our training data contains information from January 1st, 2020 to December 31st, 2023. Then our test data is all the values for 2024. So from January 1st, 2024 to December 31st, 2024, everything is our test data. So what are we doing here? So once we train the data, the model with our trained data, which is 2020 data to 2023 data, take note, just like linear regression and support vector and other models, our test data is also part of the original data set. But it's the data set we are already aware of the results. What do I mean? This test data contains the number of visitors that came in 2024. But now in this situation, we're training the data, we're giving the data, the model, information of 2020 to 2023. It is not aware of, the model at this point now is not aware of the number of visitors that came in 2024. So we're telling the model, predicts the number of visitors that will come in 2024. So once it predicts it, then we run our metrics, that is our mean squared error matrix, to check the error differences. Just as I've explained in the other video where we worked with the linear regression and support vector regression model, it follows the same pattern. So in this situation, we say, okay, so you have been able to predict visitors for 2024. So let's check. What did you predict for January 1st, 2024? Let's see what the original data, which is this test data now, which contains the already predicted 2024, that is, sorry, the original data of visitors that came in 2024. This is it here. We're going to compare it with what the model predicted as the visitors that came in 2024. So as we proceed, I will display the data set, the predicted one and this original one, and we will look at the comparison. So we trained our data, our model with this trained data. Then we forecasted for 2024. So we forecast it, we get the values, and we saved it to this CSV file. So now we are plotting it. So we are plotting to check. Let's see the forecasted value, which is this, against our test data set, the original 2024 data that we have. We're plotting it against the predicted 2024 data. So let's see how our chart looks like. So here it is. So it has been predicted, which is around 0. So now, after predicting, before we look at how to calculate the error, let's take a look at our file that was saved, the predicted. Okay, so after training our model, as we did earlier on, now we want to forecast. So we're forecasting for the next 365 days, which is for 2024. So we do the same thing. So we get the index for our trained data. So it's going to start counting from 2024 January, because our last data from our trained data set stopped at 2023. So that's what this place does. So we're just trying to get the index for our data set. So it predicts and saves it to this file. So what will be contained in this file is the date, which is 2024 date from January to December, and the forecasted value for 2024. Then we plot the forecast versus actual value So our actual value is our test data. Don't forget we split our data set. So our test data, that is the original 2024 data that we already have. We plot it against the forecasted 2024 data. So this is our chart here. So you can see the forecasted value on the blue value, which is the actual value. If the SARIMA model was very good, it's supposed to be an almost straight line. That is, the line is supposed to be close to each other as a straight line. But with these spikes, it means it didn't predict well. So we have to calculate the error matrix. So we have to calculate the error in number. So we call our mean squared error. We pass in our actual data, which is our test data, and our predicted value, which is our forecasted value. We put it into our mean square error. When we got the answer, we squared it. We found the square root of the RMSE. And this was the value we got. Now, in our previous video where we used linear regression and support vector regression for this same data set, the result we got for our RMSE was around 200 and something. But in SARIMA, we're having 416. The lower your RMSE, the better the model. So with a 416 RMSE, it means SARIMA is not good. Linear regression and support vector regression models are better. And I've already run this data set on a random forest model, and random forest did far better with a result of about 100 and something. So that is how this works. So let's go and check our data set, the predicted data set. Okay. So on my own, I had to copy the original data set and paste so that we can easily compare it. So we can see 2024. So this pack visit difference, this is the original values for 2024. But we have already passed it through the differencing. That is, we differenced our data before we finally trained our model. So this is the difference data. Comparing it to the predicted value for 2024, you can see it's saying minus 51. How can we be having minus 51? So you can see the model didn't do so well. It didn't do so well. So even though we decide to remove the minus by using modulus in our data, we can see that 51 visitors compared to 1,307 is not good at all.